So not all buffers are made by titrations. In fact, the vast majority of buffers are made just by having the acid and its conjugate base. And so the primary components for a buffer are really acid and conjugate base. So for example, if you had HF, oops, if you're trying to make a buffer with HF, that would be my acid, and then the conjugate base would probably be something like sodium acetate or sodium fluoride. Sorry, I don't know where acetate came from. If you wanted to do one with the acetic acid, since I'm on that now, C2H3O2, then the conjugate base would be something like sodium acetate, which is what I said before, because I guess maybe I've used it so many times, right? Again, uh, what confuses students a lot of times is this. It's a spectator ion, so we're going to ignore it in any of the calculations. Okay, but you need some positive ion to balance out that negative ion. So when you're making these solutions, you need the acid and its conjugate base. And then this is the part where I tell you I lied to you already. And when I was telling you this ratio of 10% to 90%, it's actually the concentration ratio that people use is 10 to 1. So that's actually the 9.09% to 90.91% ratio. But basically 10 to 1 gives you a good idea of where you find the range of the buffer. This is kind of why when we were looking back at this graph here, I didn't quite get to the pH that I needed to, because it's actually like here. The range is supposed to be at 8, and this one is supposed to be just a little bit over this way some. So that's why these didn't quite fit exactly. I know most of you probably didn't notice that this didn't go exactly to 8, because the point is actually right here. But I always find remembering like this is way harder than remembering not 10 and 90. Okay, and it's close enough and gets us a reasonably good definition for the range of a buffer. So you want to have the pH be within the range. You need the ratio to be within about 10 to 1. Okay, so let's do a problem, right? Calculate the pH of an acetate buffer solution. This is what they would call it. Now, you notice they named it after the anion, and that's almost always the case. They name it after the polyatomic ion, which is part of the buffering system. So, if we want to calculate the pH, then what we're going to do is create an ice table, okay, like this. And we're going to have our HAC, and this is the sodium acetate. So we're going to say plus water. So we use the weak acid ionization reaction, H3O plus AC minus. And this is from the sodium acetate. And then we're going to draw our lines like this. And then we're going to do initial change of an equilibrium, and man, my lines are crooked. Holy cow. And we're going to ignore that because it's the water. So I'm going to have 0.10 molar of this, I'll have 0 of this, and I'll have 0.15 molar of this, right? And then I'm going to have minus x, and 0.10 minus x, and 0.15 plus x, like that. And from this, I will be able to calculate the pH of the solution. So Ka is equal to hydronium times AC minus, because I added a C to it, and for acetate, and then over HAC. And this is going to be equal to, and then you have to look up the Ka value, right? So when you look up the Ka value, it turns out to be like the most precise one I could find is 1.76 times 10 to the minus fifth. And we can plug in that this is going to be x times 0.15 minus x divided by 0.1 where was I? 0.10 minus x. That's equal to 1.76 times 10 to the minus fifth, and then I can just solve it for x, and this will give me my hydronium ion concentration. So this gives 1.173 times 10 to the minus fifth, and then from that I can calculate, because that's my hydronium, right? I can calculate pH is equal to 4.93. All right, so this is one way that you can calculate the pH of a buffer and do buffer calculations, but there's also another way, and it's probably the more generally accepted way in biochemistry to do buffer calculations. And so what I'm going to show you next, and in chemistry, really, it's probably one of the more accepted ways as well. What I'm going to show you next is how to do buffer calculations that way. So I need to set this up for you, and we're going to start again with an ice table. And this is actually, the ice table had it all set up on another slide for this purpose. When I solved for this one, what we found was that x was 1.173, I believe. 1.173 times 10 to the minus fifth, sorry. And so think about what this value is, right? What we can do is we can do essentially what is an x is small approximation with these calculations. And this is almost always true if you're within the buffer region of a buffer. Okay, the only exceptions would be at really, really low concentrations, which normally people don't make up buffers at really low concentrations because the whole idea is they want to stop the pH from changing, so typically the concentrations are higher rather than lower. Okay, so usually this will work. 99% of the time this works. You're going to have ability to say x is small, right? And so a lot of times we just cross this out and say x is small and we solve it. So when we put it through the solver, we get a value of 1.1173, but what happens if we just solve this equation, right? So now I have this. I have x is times 0.15 over 0.10 equal 1.76 times 10 to the minus fifth, right? And then I'm going to rearrange it so it's going to be x is equal to 0.10 divided by 0.15 times 1.76 times 10 to the minus fifth. And so we'll just run that into our little super fancy calculator here. Hang on. Oh yeah, this is I was already doing some other calculations. So let's say it's 0.1 times divided by. So 0.1 divided by 0.15 times 1.76, and then I need my scientific notation button, which I believe is going to be my E. Yep. And then 5, and change sign like this, right? And hit equals. And what did I get? I got the exact same number. So in other words, we used a solver, which meant entering all this, or we could have just assumed x is small, which means rearranging this, or you could put that in a solver too, for that matter. And we get the same answer. That's because x really, really is small compared to both the conjugate base and the weak acid. And as long as you're within that 10 to 90% range, or the 9.09 to 90.9% range, right? You're good. This solution will work. Now, what is weird about this? What is weird about this is actually, if you think about what this represents, it actually is just that. It's the concentration of the conjugate base and the concentration of the acid. So really, you can do buffer calculations without any ice tables, and assuming that the concentrations don't change, you're just working with the equilibrium constant expression. So if you have this, then what you can write is, for example, if you want the hydronium ion concentration, it's simply going to be equal to Ka times the concentration of the acid, oops, I forgot my H, divided by the concentration of my A minus, like that. It doesn't require an ice table because X isn't small, so there's nothing really that you have to solve for. Okay, so this is actually a setup for something called the Henderson-Hasselbalch equation, because still in this process you still have to do the logs and all that stuff, and you still have to do all this rearranging. There's actually a better solution that was come up by biochemists, I believe, for calculating pH in buffer solutions.